Now I'm going to continue with some important topological properties of convex sets. So this is proposition 1.31 in the textbook. Let omega be a subset of Rn and we assume that omega is convex, and we also suppose that the interior of omega is non-empty. Then the following properties are satisfied. The first property is, if we take the closure of the interior of omega, then it is the same as the closure of omega. Okay, and the second property is the interior of omega is equal to the interior of the closure of omega. Note that these properties are satisfied for convex sets. We can easily find counterexamples to show that these properties are not true in general for non-convex sets. So now let me go through the proof of this proposition. The proof is heavily based on the previous lemma. So obviously, the closure of the interior of omega is a subset of the closure of omega. This follows from the fact that the interior of omega is always a subset of omega. Okay. Now we're gonna prove the opposite inclusion. So we will show that the closure of omega is a subset of the closure of the interior of omega. Okay. So we're gonna fix any B in the closure of omega, and our goal is to show that B belongs to the closure of the interior of omega. Okay. Now here we have this assumption: the interior of omega is non-empty. So since the interior of omega is non-empty, there exists an element A that belongs to the interior of omega. Okay, now as B is in the closure of omega, since B belongs to the closure of omega, we can find a sequence in omega that converges to B. There exists a sequence Bk in omega that converges to B. Okay. In the next proposition, we're gonna establish some relationship between taking the interior and closure of convex sets. This is proposition 1.31 from the textbook. Let omega be a convex subset of Rn. with non-empty interior. Then we have the following properties. The first property is the closure of the interior of omega is equal to the closure of omega. And the second property is the interior of omega is equal to the interior of the closure of omega. Okay, so now I'm going to go through the detailed proof of this proposition. So let's prove the first property. Obviously, the interior of omega is a subset of omega, and hence the closure of the interior of omega is a subset of the closure of omega. Let us now prove the opposite inclusion here. Okay, so now we're going to show that the closure of omega is a subset of the closure of the interior of omega. And to achieve this, we're going to take an arbitrary element of the closure of omega, and then we show that it is in the closure of the interior of omega. So fix any B in the closure of omega. Now we're going to use the assumption that the interior of omega is non-empty. So then we can fix an element. Fix an element A in the interior of omega, and then we consider the following sequence. Define the sequence. Xk equals to 1 over k times A plus 1 minus 1 over k times B. So by lemma 1.30, xk belongs to the interior of omega for all k in n. Note that here B is in the closure of omega and A is in the interior of omega. So if we take any lambda in the open interval 0, 1, then lambda A plus 1 minus lambda B belongs to the interior of omega as in lemma 1/30. So in particular, 1 over k times A plus 1 minus 1 over k times B is in the interior of omega. Okay? And then observe that xk converges to B as k approaches infinity. So if k approaches infinity, 1 over ka approaches 0, and 1 minus 1 over kb approaches b, therefore xk approaches b as k approaches infinity. Therefore, b belongs to the closure of the interior of omega, because we can find a sequence in the interior of omega not converges to b. Okay, so here we take any b in the closure of omega, and we have showed that b belongs to the closure of the interior of omega. So we have showed that the opposite inclusion here is satisfied. That means the closure of the interior of omega is a subset of the closure of omega. So the proof for I is complete. Okay. Now we're gonna prove that the second property is also satisfied. Okay. First, we see that since omega is a subset of the closure of omega, if we take the interior of omega, we have a subset of the interior of the closure of omega. Okay, so now we will prove the opposite inclusion here in order to establish the equality in double I. Okay, so let us show that. The interior of the closure of omega is a subset of the interior of omega, and we're gonna prove this by taking an arbitrary element in the interior of the closure of omega, and then we show that it is in the interior of omega. Okay, so fix any element b in the interior of the closure of omega. Okay. Again, we're gonna use the assumption that the interior of omega is non-empty. So we can take an element A in the interior of omega. And here, and fix A in the interior of omega. Now, because B is in the interior of the closure of omega, if epsilon is sufficiently small, then we have the following. The element C defined by B plus epsilon times B minus A belongs to the closure of omega. Okay, so this is the closure of omega, and then B belongs to the interior of the closure of omega, and A is in the interior of omega. So B minus A, so if we take a B and we add epsilon times B minus A, so here is B. If we take a B and we add epsilon times B minus A, then we still have an element C that is still in the closure of omega. Okay, so because when epsilon is small, we can take epsilon times B minus A can be made such in a way that its norm is arbitrarily small. So it will be in the the closure of omega. From here, we're going to have the following. Then from this equality, we have that C is equal to B plus epsilon B minus epsilon A. Okay. So then we can solve for B by doing this. So then we have C plus epsilon A is equal to 1 plus epsilon times B. Therefore, B can be written as 1 over 1 plus epsilon times C plus epsilon over 1 plus epsilon times A. Okay? So, this is just a convex combination of A and C, because the sum of 1 over 1 plus epsilon and epsilon over 1 plus epsilon is 1. Therefore, this element belongs to the open interval AC. Okay? And by lemma 1.30, here C is an element in the closure of omega, and A is an element in the interior of omega. By lemma 130, this open interval belongs to the interior of omega. Again, here we use lemma 1.30. Okay, so we have showed that if we take an arbitrary element B in the interior of the closure of omega, then B belongs to the interior of omega. Therefore, the interior of the closure of omega is a subset of the interior of omega. Okay, so the proof of the proposition is complete.